Greetings, Statesmen. Today we're going to discuss graphing equations in slope and intercept form. Slope-Intercept Form, excuse me. First thing we want to discuss is the idea of slope, which we haven't really brought up too much. Slope mathematically gets the distinction commonly with the variable m, and what it means is that it's referring to a line where we're going to figure out its change through the rise over run, right? There's a vertical change, the rise, and a horizontal change, the run. It's the change in y, the vertical change, over the change in x. That little triangle is the Greek letter delta, standing for change. It's something you will commonly see in science classes like physics. And to calculate that change, if we take 2 points on that line, we're going to subtract difference of the y's, y sub 1 and y sub 2, over the difference of the x's, x sub 1 and x sub 2. Now it's imperative that we keep those in order. Not that it always has to be the first y or the first x first. What's also permissible is the following, is that we could have y sub 2 and subtract, not x, but y sub 1, and always have it with x sub 2 minus x sub 1. The big thing is that if we go first, right, y sub 1 first, it has to go first minus second over first minus second, or it has to be second minus first over second minus first. That's what the subscript is referring to. Whatever we make a distinction is the first or the second point. For the record, it doesn't matter as long as we're consistent in what we're identifying as what is first and what is second. Moreover, it always has to be the vertical over the horizontal change. In other words, you always have to have your y's over your x's. On a coordinate plane, what we would observe is the following. You'd have, again, the y and x axes, and we'd have a line that's illustrated on there. You know, I'm going to make that line a little different color, just so we can see that it's not confusing it with the axes of the coordinate plane. Now let's say that we take 2 points on that line, okay? The change there, again, there's going to be a vertical change here, which we refer to as the rise, over this horizontal change, which we refer to as the run. So again, it's going to be that vertical over the horizontal increase is how we're going to account for that mathematically. Next, we're going to examine the 4 types of slope. Typically, I always cite one of my favorite video games of all time, Super Mario Brothers, as to help us distinguish some ideas with slope. Because I think sometimes kids get confused about if they should be rising or running, and if they're going forwards or backwards or what have you. In the game Super Mario Brothers, one of the things about the character is that he only is capable of going right. I know there's sometimes it's considered to be that, oh, the objective of the game is that you're supposed to collect coins and save the princess. But really what we're doing is that we're just moving right. In fact, in that game, it's impossible to go back left once you have moved the screen to the right. When we are looking at slope, we're going to consider this going from left, always moving to the right. We're always going to run forward. So the first type of slope we're going to look at is this one here in the top left corner, which is what is known as a positive slope. These are positive because the outcome of m, when we calculate it with real values, a real number, right, for the rational expression of y over x, always going to have a positive outcome. Even if it's a fraction, it's always going to be positive, okay? I always think of it as positive because it's always going up, right? So this is like going uphill. If you're walking uphill, you'd be increasing in altitude. Therefore, you'd have your elevation is going to only be positive, more positive. Then we have a negative slope, illustrated here in the top right. The negative slope is when we calculate m and it winds up being a negative number. It doesn't matter how large the negative number is or how small the negative number is, right? It could be a million, it could also be a fraction. But the outcome of when you take y divided by the change in y divided by the change in x, it winds up being a negative outcome. Again, this guy right here is downhill from left to right. As we go from left to right, we're decreasing in altitude. Next is this guy, which is known as zero slope. Some people will say no slope, but again, it's where there's no vertical change, right? So in other words, that change in y is going to be 0, and you divide 0 by anything, the outcome is going to be 0. It's kind of like thinking about flat land, which is like saying there is no slope to it. Yeah, so we're moving along with flat land that has no slope, which is 0 slope, okay? Now, the last thing here is this straight up and down vertical line, which is the undefined slope. Now, think about this. If you were to, again, we don't have any horizontal change, okay? The horizontal change is fixed. So that means that if there's no horizontal change, there's no change in x, meaning that we're trying to divide by 0. And in this case, we'll take a, which is any real number, and we're going to divide it by 0. Now think about what the outcome is. Can you divide by 0? Mistake people make is they say it's 0, and that's not true. Go punch it into a calculator. It's impossible. It's not defined, right? And think about how we would even define that slope for us to walk on it, right? A positive, we're going up. The negative, we're going down. The 0 slope, we're just moving right along without anything impeding us. But you can't walk on that vertical line. It's impossible. So it is undefined. Next. I'm going to take this problem here. We have illustrated a coordinate plane with our y and x axes, and we're going to graph some points. The first one is the point 1, 3, and the second point is -2, -3. And if I were to make a line through this, right, this line surely has a slope that we are going to find in this case. Now, sometimes students will say, well, can I just count those spaces? That's not what I want to do in this exercise. Here, I actually want to employ the slope formula. So we're going to say m, of course, which is equal to y sub 1 minus y sub 2 over x sub 1 minus x sub 2. And we're going to employ that formula here for these 2 points. Now, we need to go ahead and label our points. So let's take 1, 3. This is going to be our first point. It doesn't have to be. We could use the other one. The outcome is going to, the -2, -3. The outcome will be the same, though. Watch. So, and I'll demonstrate that shortly. So this is going to be x sub 1, meaning this has to be y sub 1. Remember, in ordered pair, it is alphabetical. It's always going to be x comma y. So here, that was my first one. It means that -2 has to be x sub 2, and -3 has to be y sub 2. Has to be, has to be, has to be. Okay? Because the other one has already taken the place as the first point. So let's substitute. Y sub 1, we had 3. Okay, and remember, when we substitute, we do so in parentheses. Minus -3, my y sub 2, over x sub 1, which is 1, minus, and then my x sub 2 is -2. Now remember what happens here. I have 3 minus -3, and that's going to be plus, or 1 minus -2, which is also going to be plus, or in other words, 6 over 3, which is just 2. That's my slope. Also, that's how I just write this, because you don't just write the number 2 over 1, but the slope, how we'd execute it in a coordinate plane is it's really going to be a rise up and down, a rise up of 2, and then a run right of 1 space. So it's 2 over 1. Remember, any real number that we take over, any real number we can take as an identity by divide by 1. So everything is divided by 1. The number 10, for example, is the same as 10 over 1. Just kind of, you don't have to necessarily write this down, but just further proof in terms of how we could have employed this. We could have switched this guy up. We could have used the other formula, y sub 2 minus y sub 1, and x sub 2 minus x sub 1. Now think about this. If we had labeled this thing differently, right, where -2, -3 were actually my y sub 1, y sub 2, I would have done this formula actually in this way, right? I would have subtracted first, I would have taken my -3, and then I would have subtracted 3 all over my x sub 2, my -2, subtracting 1, right? Which is going to give me -6 over -3. And again, it's the same exact answer. So it's pretty forgiving in that way. The big thing is that we don't mix up and say we do, always has to be y over x. If you do it the other way around, if it's x over y, that's going to be incorrect. Your slope's going to be upside down. And then the other issue is if we go y sub 2 minus y sub 1, but then we have x sub 1 first. That doesn't work, right? We always have to consistently subtract one point from the other. Next, we're going to look at a couple tables here. X over y, we have -3, -1, 0, and 3. Then y's, I have -1, 3, 5, and 11. And what we're going to do here in our directions is it says that we are going to find the slope from the table that represents points on the line, okay? So all we have to do is take, and it's already been distinguished that these are points in a line, so all we have to do is just pick two of the points. So let's just pick the last two. It can be any two, it could be the first two, right? And we're just going to plug them into the slope formula, right? So y sub 2 minus y sub 1, just practice this over again, over x sub 2 minus x sub 1, which is going to equal, right? It's going to be 11 minus 5, right? Over 3 minus 0, which in this case winds up being 6 over 3. And again, just happens to be 2. So there's our slope. Let's do another one of these. So in y, so we have -4, 0, 4, and 8. And then on the y's, we have -2, -2, -2, -2. Now notice there's no vertical change. So what that's going to create is a horizontal line, right? No vertical change. It's going to look like no vertical change in a horizontal line is going to be 0 slope. So we should have 0 as our outcome. Well, let's take a look. So m is equal to, we're going to take, let's take again these last 2 points, right? We're going to take -2, right? Minus 2, and we're going to put that over 8 minus 4, okay? Right, the second x minus the first one. And then, well, -2 minus -2, it's going to be -2 plus 2, which is 0, or 0 over 4, which of course the outcome is just 0. That is 0 slope, okay? Totally works that way. One more of these, x and y. We're going to have inputs of 4, 4, 4, and 4, -5, -2, -1, and 4. Now remember what we discussed earlier, and this time actually I'm going to take the first 2 points, because why not? You can do any two. We'll work with the first two. Discussed earlier in this chapter that if I have an input that has multiple outputs, then that's not a function, right? It would fail the vertical line test. If it's not a function, which this is going to do that because it is a vertical line. A vertical line will intersect a vertical line at all the points, right? Not just a singular point. It's going to intersect, in fact, an infinite number of points. So here we have 4, right, is the singular input. I write it multiple times, but I have all these other outputs. Let's take a look at what's going to happen here. Remember, the vertical line that we assume, because there's no horizontal change, is going to be undefined, meaning we'll wind up dividing by 0. So let's do this mathematically. Let's take the first one, right? So -5, and we're going to subtract -2 over 4 minus 4, which we're going to get -5 minus -2 is plus, so this is -3 over 0, which is the answer, right? That's undefined. You cannot divide by 0. All right, next, let's discuss the slope-intercept form of a function. Which is that y is equal to mx plus b. Discussed this before, it's also the function form. We have the dependent variable y depending on the outcome of whatever we're going to put as our input, that independent variable x, okay, in that function. Here are the elements, the other elements. We have m, which we already know, that's the slope, as we discussed earlier. B is that what we know is the y-intercept. And we don't use y, right? This is one of those things that makes sense, why mathematicians set this up this way. You're not going to use y at all in there because you already have a y that's your output. So that would be really, really confusing. So in this problem here, let's take a look at something in slope-intercept form of y is equal to 2x minus 3. Let's identify what my slope is and what my y-intercept is. Well, here, my slope is 2. And simply put, my y-intercept is negative 3. It's this number that follows mx. Rather straightforward. Let's look at another one. How about y is equal to negative 4.5? Now notice I am lacking a term multiplied times the independent variable x. There's no m or x, right? Well, what that means is that m would have to be 0 multiplied times x to cancel x out completely. So really, I don't have a slope here. My slope is 0. And consider this. If you were to graph that, that's going to be a horizontal line, right? Through that on the coordinate plane, right? Through negative 4.5 on that y-axis, and just going to go straight across, right? Negative 4.5 all over and over and over again. In fact, since that's also going to be my y-intercept, right? That's the singular place where that's going to go through the y-axis. Last one we have here. 6x being equal to 8. I'm sorry. Let's do this in standard form. 6x minus y being equal to 8. Again, standard form, right? ax plus by equal to c. So let's fix this. We need to solve this equation for y. We need to make this equal to y by itself. Okay, so I'm going to do that. I'm going to get y by itself. I'm going to move it over to this other side, right? So I have 6x is equal to 8 plus y. And then to get y by itself, I'll get rid of the 8 on this side. So I have 6x minus 8 is equal to y, which we really know symmetrically is just that y is equal to 6x minus 8. And there we go. Now I'm in slope-intercept form, and I can very readily identify what my slope is, right? When I make the whole thing equal to y, right? Function form. Also slope-intercept form. So my slope is 6, and my y-intercept is negative 8. All right. Next, we're going to graph 2x plus y equaling 2 using slope-intercept form. Okay, well, it'd be ideal if we were in slope-intercept form, so let's go ahead and do that. Let's go ahead and subtract 2x from both sides, okay? And then we have y is equal to negative 2x plus 2. So, as we get to solving this, right, let's create my coordinate plane. My y and x axes. And I'm going to have a slope, right? Because this is going to work like Google Maps, right? Our slope is actually going to wind up being our directions, but we need a beginning destination, which is what our y-intercept will be. So in this case, it's negative 2. But remember, what negative 2 means in terms of rise over run, it's going to be negative 2 over 1. Now, remember what I said about Super Mario. We're always going to run right. If we're running right, we're always going to move in the positive direction horizontally, okay? So all of the negatives, when we do these problems, I want us to apply these to the numerator. That way we're going to rise and fall, but we're always going to run forward, okay? A little bit of a metaphor for you there. Moreover, I have the y-intercept, which is 2. So that's my starting place. I know on the y-axis, boom, right here, this is where I'm going to start. And then I'm going to go down 2, and right 1, right? That's my rise and my run. So get that line. Now, you don't have to have those when you guys are actually completing these problems. I just need you to plot that second point. Boom. Connect my 2 dots. And there I have my graph. All right, 2 more of these examples. these are going to be a little bit more of word problems here. Next thing is a linear function g models a relationship in which the dependent variable increases 2 units for every 3 units that the independent variable increases. We're going to graph g when the g of 0 is equal to 2, and we're going to identify the slope, y-intercept, and a new one for us, the x-intercept. Fun. Let's do it. First of all, let's create our coordinate plane. Y and x. My dependent variable, remember what that means, that's y. And independent, because y is going to depend on whatever we're going to input for x. So y increases 2. In other words, we're going to go up 2. Oops. We can't do that. We don't have a y-intercept. Well, let's see what this is. It says the g of 0 is equal to 2. You know what that means? Remember, from notation. That means when the x is equal to 0 and the output will be 2. So what's nice about when we have that function notation, it looks just like the coordinate. The g of 0 equaling 2 means 0, 2. So coincidentally, that winds up being, our y-intercept. Now, we're going to increase. We're going to go up 2. Okay? And our run is going to be 3, because it says 3 for the independent variable. So 1, 2, 3. We're going to move forward x with 3, right? And then we're going to connect these 2 points. So, my slope, it's the rise 2 over the run, which was 3. That's how I figured it out. I didn't do a calculation. Though I could identify this point right here, right? Which is 3, 4. I could do that and then figure out the difference in the slope there, right? 4 minus 2 over 3 minus 0. You could do that. But in this case, because of the way they describe the problem, we know we're going to have these vertical, they very explicitly describe the vertical and the horizontal changes. The y-intercept was very straightforward. It was 2, right? It's the x-intercept we don't have yet. Remember what the x-intercept will be. Take our function, the g of x is equal to, well, it's 2/3 the slope, mx, plus b, the y-intercept is 2. So if we can figure out where y is equal to 0, right, we can figure out what this point is down here, okay? It looks like right now it's 1, 2, 3, but that's just because I'm throwing up slashes and I happen to meet there. It might not be, so let's actually go ahead and figure out where this function is going to be equal to 0, right? Where the y value will be 0. And then we're going to solve for x, right? In this case, and this is, of course, on the x-axis over here. So yeah, let's go ahead, and we're going to have negative 2 is equal to 2/3 x, and then we're going to multiply by 3 over 2. Right? And the 2 is going to factor out, so I'm going to have a negative 3 is equal to x. So my x-intercept is negative 3. Excellent. Last part of my problem is that we're going to take a look at a submarine problem. So the elevation, h, and of course this is in feet, of a submersible is modeled by the function h of t equaling 550t minus 11,000. where t is the time in minutes since the submersible began to ascend. We have a few things we have to accomplish here. A, we're going to graph the function and identify the domain and range. And then we're going to interpret slope and the intercepts of the graph. Okay. We're going to use a scale here, because that's going to be the best way for us to go about this. Okay, so we already have this guy, we already have a function here. Let's go ahead and do this. And when I make this, I really need this, this fourth quadrant really identified well here, okay? Sorry, second quadrant, I'm sorry. So this is going to be, rather than y, right, and x, well, we know this guy is t because that's my independent variable. So we're going to make this other guy h, the h of t, okay? And we're going to go down 11,000. So I'm going to count by thousands. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is going to be my y-intercept. And then over here, I'm going to wind up counting by, I got to figure out where my t-intercept is going to be, right? And where I'm going to wind up figuring out that t-intercept is, it's going to be where that function is going to be equal to 0 again. So it's going to be equal to 550 t minus 11,000. Okay, so now I'm going to solve for t, right? 11,000 is equal to 550 t. And then when I divide both sides by 550, right? 550, 550. This guy is going to be equal to 20. So t is equal to 20 in this case, okay? So it's going to be here. It's going to be 20 comma 0. So 1, 2, and let's count by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And that's going to be my second point. So here we go. Let's go actually and connect these two. Now it's a submersible, right? So if it reaches the surface, it can't go above that, like if we're talking about water and it's a submarine. So we have to think about what's realistic for that height. First of all, we have to think about domain. If we're talking about time, okay, of course we can't go any more negative than 0, right? So it's just, there's the starting point 0, and it's going to include that less than or equal to t. It's going to be between 0 and this right here, which we know is going to be 20, versus our range, right? Which we know it's going to be from here all the way to how much is represented on the graph. It's going to be negative 11,000, less than or equal to, in this case, h, and then the surface, of course, less than or equal to 0. So between negative 11,000 and 0. So our slope and intercepts, my slope, of course, was 550. My t-intercept, okay, was 20. So in other words, this was 20 minutes until the sub reaches surface. And then I have my h-intercept, which of course is negative 11,000, right? And that's where the sub begins, at negative 11,000 feet. Okay, your assignment is on Canvas. Go ahead and tackle that, and good luck.